So it's a presentation where I show a lot of different things, not in depth, but hopefully in an articulate way, touching a lot of issues that we have had regarding recommender systems, evaluation, the links to diversity exploration, etc., and the connection with HinPy and Juggle. So it's a very it's a mashup of a lot of things. So I want to present recommender systems, well, what it's out there, because there's a lot out there. It's too much out there. So I try to provide some kind of grille de lecture for it. Then to talk about how to evaluate, to brush on this thing about accuracy and diversities, and to talk about the things that inspired HinPy, and then the connection to HinPy. So in this first part, it's not a presentation in depth, but I hope to cover what is known now as classic recommender systems, and then the more modern stuff that it's more trend on these AI journals and conferences. And then on the evaluation, I'm very much focusing on accuracy, because it's a thing we talk about, how to measure performance. And then the diversities, before all, that's a problem, because this is a continuing problem in the recommender system community, and it's linked to the quality and industrial setting, but also to other problems like filter bubbles, echo chambers, discovery and innovation, in our case, in collective intelligence. And then this fourth part, which is the inspiration for HinPy, is how to exploit a lot of things that exist in here to provide an answer to the question of how to define these diversities and how that connects to HinPy and the Juggle recommender system. So there's a first part of the history of recommender systems that's from mid 1990s to mid 2010s, which is the basic idea that you have too many things in life, you have limited time attention, so you need to select. And the first attempts were made, the first famous attempts, landmarks attempts, by this group lens, which are the authors of the very well-known datasets, movie lens. So what they start doing is topological recommendation. That means recommending neighbors. So you have here, for example, some users. This user has used these two items. So user-based collaborative filtering recommends items that have been used by users that use the same items you use. So it's neighbors in a projected network. Or the other way around, you can do, here is like similarity of items because of users. Here is like similarity of users because of items. So this is, for example, what Amazon used. So you can recommend things that have been used also by, but there are neighbors on the projected network. And very similarly, if you included, for example, users, items, and some sort of content or type of item, you can do some topological operations to discover what are the items that are neighbors to the items you chose in this projected network between items and content. So this is the basics, the origins of what's been done, with all topological. And then people began giving signals back, not only implicit. Yes?
Can you just come back before, sorry, the third one? So I understand the projections before, and the last one, there's three. What is a dashed line exactly?
The last dashed line is you establish a connection to a type implicitly because you chose an item of that type, which could be invisible to a user. But you could want to account for that in your topological recommendation.
Okay, I understand. Thank you.
So then people began recording signals, input signals from users, for example, giving stars, giving scores. So before you had implicit signals, binary signals, like you used something or not. This is called implicit in the recommender system community. And they start recording explicit, which are ranking. Typically in the movie lens that everyone knows is score from 1 to 5. So you have a metrical dimension now to the recommendations. So for example, in here, a classic metrical recommendation using an extension of these collaborative principles are users gave scores from 1 to 5 to items. You arrange those in a matrix, and then you can compute a row-wise similarity using cosine similarity, for example. So in here, for example, you have user 4, and user 4 has his row and can be computed similarity with other users using some kind of, here I think it's cosine similarity. So you choose the rows that are more similar to you, accounting by what you were doing before topologically, but also metrically, because you have numbers like weights in your
and what do you do? And what do you do when you have no numbers, like in Netflix?
You have no numbers?
Yeah, I mean, the missing values, you just put them as zeros, right? Or you...
Yeah, actually this idea spurred the metrical recommendations with implicit. Implicit, it's like you said, binary. So you force some metric into this. 0 is haven't seen, 1 is seen, and you compute cosine similarity again. And with cosine similarity, with a matrix of only ones and zeros, you can compute users similar to you and use that as your clique. In here, you would have had a clique based only on topological concepts. In here, you could have a clique based on metrical concepts. So a clique is a group of users similar to you, and you use things that they chose to recommend things to you.
Mm-hmm.
And this idea was at the core of what Amazon did for a decade almost. So Amazon had a huge engineering system where they had a catalog and they computed item to item similarities.
But
So
just going back to the question of Luba, I understand that there's a problem of if somebody did only 2 or 3 items in their lifetime, but they are very similar to mine, and I did 300, it's not the same that it could be the same cosine similarities and somebody that also did 300 items, but does it take into account that absolute number of common items?
in here, there's a world of people doing tweaking and engineering, like a decade of people doing tweaking and engineering on similarity measures between rows.
I see.
Like you have a list of papers that review 15 similarity metrics between rows, accounting in these little details.
Okay.
I'll put I put a slide about with all those references.
Okay.
But this is a detail worth noting that this simple idea really was the gagne-pain de Amazon for like a decade, like keeping a very a good up-to-date similarity in between items. So you had little signal from the user. You were inspecting one item, and right away you could have other items to be recommended to this person.
Yeah. Pedro, tell me if I'm wrong, but this is also what like the Netflix challenge solving problem was of a very similar nature, where you had users' movies, and it was a sparse.
Here. It was my next slide.
Sorry, yeah, they don't want to steal your presentation.
Don't worry. So people in the community, which is very driven by industry, had some kind of taxonomy of what recommender systems are. Those in here were called memory-based recommender systems. And here are what are called model-based, which means you have that bipartite or matrix represented the bipartite, and you try to do a model of it instead of mining for similarities in it. So for example, the model from this famous Netflix prize was some sort of matrix factorization, so that it would give you, multiplying these factors, the missing values for this matrix. So typically, if you do some kind of factorization, the new dimensions that are appearing here are latent features of something that defines what people base their choices on. So people have tried to compare these latent factors to things that could be measured, like what actors were in films if these were users and films being recommended. So the most famous idea is this matrix factorization, of which several flavors exist, alternating least squares, singular value decomposition, and this one, which is the one from this prize that was organized by Netflix, where they opened a huge database and people were challenged to produce recommendations that had the minimal error in the score that people would give to a film. And this solution with non-linear, non-negative matrix factorization achieved, won the prize because they were down to, I don't remember, but it was around 0.4 or something out of a rating from 1 to 5, something like that. But the interesting thing is that they never used the result, because doing recommendation like this, being very accurate, it's not very a good idea. It's not what people want. When you receive very accurate recommendations, it's very annoying. You see a lot of evidence stuff. It's not useful recommendation. I want to talk about that a bit later. So there are a lot of other flavors that you're going to find included as model-based. I'll give in here, for example, I have this paper that tells the story of the first decade very well. It's very schematic. It shows the database used, the thing we discussed about mining, similarities in matrices, and this part about models. So in here, for example, it shows, this figure is from this article. So it shows what it looks like, the pipeline. So you have your databases, you have your flavors of models that are collaborative or content-based. And at the time, people made the distinction about democratic filtering that would now be something like content-based for users. Like you have content for films, if they were horror, terror, France, Spain, US. Now they have content for users. So you have your classic memory-based similarity measures between users and items, and there's another way of doing things, applying these methods that are in the model-based. You do your predictions, you have your model that allows you to do predictions. You test if your model is accurate enough. Then you produce recommendations and you apply different metrics to see if recommendations are good enough, if they are relevant. This distinction is important because in here you have a model to do recommendations and you test it, and here you have recommendations and you test if they're ranking the good order, for example. So this is the world up to 2010. This is a good book about this period. There are a lot of books out there, and they're all kind of the collage book, you know, like people, they invite 15 people to write chapters and they patch everything together. This is what the best between those books, I think. And also most of these things are implemented in Surprise, the Python model, which is also most of them included in HimPy. So for example, in a juggle him, we could compute a lot of these things taking just a bipartite part.
So I have a question.
Me too.
Like, sorry. So the question is simply that, I mean, I don't expect you to answer it, but the point is that you just said if the recommendation is good enough, and I'm always curious about like the fact that how do you decide what's good enough? Like, is there a standard metric that you can calculate, or some practices or something?
Yeah, I included this in the plan as evaluation of recommender system, which is a very debated topic. But in here, when I'm saying good enough, is in this view of things that is very well summarized in this article, the focus of the academic community and industrial community is in here.
Okay.
You see my mouse, right?
Right.
Yeah, so in here you have your model that would allow you to do recommendations, and you test the prediction capability of your model. And in here, classic things are root mean square error, for example.
Yeah.
So you're predicting how many stars someone would give to a film. You do some root mean square error from your model. And then there's another layer, but I'm going to explain that in detail later, is what actual recommendations should be evaluated on, which is the different thing.
Cool, thanks.
This is the worldview of that time.
Yeah, I had another question, Pedro. I was wondering if you know, the work that started on model-based recommendation systems, what were the motivations? I think maybe scale was probably a big factor. Maybe I'm wrong, but are there other recommendations like better accuracy, things like this, or why did this happen actually?
Yeah, I don't have positive knowledge on that, but I would think that it is because at the time there was the machine learning community developing. So there were a lot of tools and people eager to bring things from this community to the Rexis community to try these things.
Okay.
And does it also include this type of more recommendation system? Do they include evaluation of recommendation? For example, you recommended me to buy, I don't know, some book, and I really don't like this book. And where this enters here?
It enters in two types of signals that are captured in this philosophy, which are explicit and implicit. So explicit is mining the ratings you give to things, to the stars. Mm-hmm. And implicit is mining what you do or don't do. So mining positive feedback or absence of positive feedback. So that what's normally contained in this kind of data sets, or what engineers in this in Amazon have their disposal to compute recommendations.
Okay, thanks.
I think another reason why people also like model-based learning, that it allows with careful crafting to extract semantics out of those vectors, right? Like what you were saying, Pedro, which is like, you know, some people are trying to see if in the movie lens thing, like, are those vectors corresponding to like similar actors or genre, like sci-fi versus drama and things like this. So like you can abstract and craft semantics that are often hard to extract from the data set itself, right? And this is the reasoning behind algorithm today, such as like word2vec and things like this, which try to create semantic vectors of complex objects. And so model-based recommendation is one of the way to do this if done quickly. I think that might also have been one of the reasons why people started to move towards those. But I mean, I might be wrong on that.
And like I had like a very absurd reasoning, but I'll try. So like in this diagram here, the model-based thing like covers all the hybrid filtering approach, but the memory-based and like all the levels above are only collaborative filtering. So I would expect that since collaborative filtering can be solved by using matrix factorization and like basically purely mathematical approach, it might be it might make more sense to not use genetic algorithms there, for example.
I think that this classification here, it never made much sense. It emerged in in practice in industrial settings. If you, when I first started reading about these things, I found it to be really very confusing. Like, why in here wouldn't you call this? Why would you make a distinction about mining similar rows and mining factorization and calling one collaborative and the other not, or less? But in here it's implied that this is purely collaborative. So it's not a good taxonomy. It's not very consistent, I think.
That's why you have a second part called after 2010, right?
Yeah, because people are gradually abandoning this. So in the second part, what happened is that people were going crazy about networks. Networks were trendy, and people were developing artificial intelligence. They were all moving towards some kind of neural network architecture. So all this world inherit about the ones that did matrices, the one that did bipartite graphs was left behind. So the main data object in this world is the heterogeneous information network, which is it sounds a lot more fancier than it is. It is a very, very simple idea. It is only that it was resuscitated at some time in which it managed to gather some momentum and spur people in some direction, and people use it and they align themselves with this philosophy. But it's very a graph that it's colored and it has some a little more restrictions. But would you see here what it is? It is you have your entities that are grouped in entity groups. You have links that have some meaning. Links are grouped in relations. So in here you have the group of users, the group of movies. You have the group of these links that could mean, for example, people have seen these movies or people have rated these movies, some relation. And you have some other things that would have seen before as metadata, and there was not a unique structured way of viewing all this. So in here you can mix the collaborative part, because in here you have your bipartite graph, which is representable as a matrix, and all these things that before people considered as metadata now are very well organized into the same data representation, the heterogeneous information network. And it has this schema that represents the semantic of what is encoded in here. And what people did was try to mine this semantic, because now you have, if you have all your data organized in this knowledge graph of what you're modeling, and you look at the semantics at the schema level, different metapaths encode and allow you to compute encoded semantic things. For in here, like which occupations choose more certain genres depending on what users choose through their movies, right? So in here, people now gather these things, maintain these data structures, and they do mainly 3 tasks that explain, if not all, the vast majority of what's out there and what papers are about. So a first task is, once you have organized all your data set in this ontology, you can choose to select some of these links to extract things that you would use with classic methods. For example, in here, you would have users that have locations, that choose some songs and have seen some films, and you mix some of the classic methods, for example, collaborative filtering or whatnot. You mix it in. There's a lot of ancient literature on how to mix things, and now you produce an improved recommendation, because you can see users that are similar in what they like in music, and think that would give you an idea of what would be something to recommend as a song, for example. And here's a very good example of that. And this is an issue of the first kind of issues that came with this this vision of heterogeneous information network to overcome some problems. Like, for example, you want to recommend a film to someone that hasn't seen a film, but you know users that are very similar because you have some similarity.
Does it mean that you basically need to understand also, or to train how much in depth you need to go? Like, because not all the paths, right? Maybe I have changed. In the past I was choosing some stupid books. Now I'm choosing also stupid books, but different stupid books. So like, how does this method account for that?
People do account for that, but it's not a problem of this. It's also a problem in here and all along.
Okay.
And throughout all recommender systems, the quality of the signal. Mm-hmm. So this is only a way of encoding that signal. Not. It says nothing about the quality of the signal.
So I think Luba, what you're meaning here is that we're not at a steady state, right? Our tastes change in time, and the question is, are we able to identify periods that are significantly homogeneous in our history so that we limit ourselves to the last n month of a person because they are consistent, right? So I think it's a question of dynamics, right?
Yeah.
But before you were talking about the difference between 2 points, and here you talk about difference between trajectories, right? I mean, or parts of a network, right? Here, which you showed in the previous slide. But maybe I should shut up and let you continue. You'll explain.
But I think I see what you say. I think it's not related to this way of encoding. It happens whenever you have recommender systems and an input signal. And what people do, for example, one thing I've seen people doing is trying to detect some abrupt changes in time, so as to cut a person's model into time windows. For example, that's a solution I've seen in Deezer, for example, I think.
Okay, thanks.
So using these data structures, there's also all 2 tasks that are behind recommendation. The second is one of looking for similarities. So for example, you have a meta path and you can mine the similarity in users through what nationalities of actors of the films they like. So you can exploit the semantics of a meta path to mine similarities in some object group and use that to recommend things. So for example, if you want to tweak your recommender system to give more importance to this semantic encoding encoded in this path, you can do that by finding clusters or similarity measures, and then doing some k-top extraction, like you would have the similarities for all the films, for example, and you rank the top 10 and you recommend that. And the landmark paper for doing that is this one. And it is in here. Yeah?
This one is not completely different from the third example of your first slide, which was that not bipartite, but where you began to go into the topic aspect, like the tripartite network. It's not different. Or
it's not that different.
Okay. It's just that you can have any depth, not just tripartite, but you could go up to any depth.
You can have any depth and any mix of paths, as we do in Juggle.
I see. Okay. It's really network thinking. I understand.
Much more semantic and much more obvious semantic. That's the beauty of this approach, is that the semantic is encoded versus discovered.
Yeah. Very good.
And the other task that dominates in articles and recommender systems is embedding your whole heterogeneous information network and then feed that into some kind of architecture for neural networks and train your model to do whatever you want to do. And both in here and in here, the way of computing, of giving some data structure to the semantic content encoded in a metapath is doing random walks. So you have your meta path, and you do a random walk to discover, to put some kind of score in nationalities here for different users. So if you see a lot of films that have French actors, you would have a huge score here in France. And that it's encoded in embeddings or in clusters and fed into some kind of a top K extraction or some training task in neural networks. So this is what a lot of papers do.
Would it make sense, Pedro, to actually do something like this as a sort of first pass data exploration on the Joggle set? You know, like embedding, looking at some sort of, I mean, I come from the biology and big data and biology where we start by embedding. Like that is the very first thing we do, is we first embed our data set to just even look at or high dimensionality stuff in a sort of comprehensible manner. Joggle data set right now is a little similar to this, because we're starting to have a largish data set that's becoming hard to look at manually. So would embedding our users and trying to like look at like user skills, things like this, like, you know, like would it start to make sense to even start to conceive our meta path, you know, try to look at it that way? I don't know.
Yes, actually, HIMPI, it was developed as an analysis for heterogeneous information networks, and thus provides building blocks for doing that. And I have an example at the end. But yeah, it's definitely a thing that we would want to explore in as a meta study part of Juggle.
Yeah, I think, Leo, that's kind of what we've been doing already when we do bipartite projection of skill network, etc. It's just that the more high dimensional you go, the more you have to have a predefined idea of what you're looking for. And in biology, you have case control studies all the time, and that's why you're clustering, because you have cell type versus other cell type, etc. So you want to confirm intuitions. Here, we're in a process where, I mean, you know, there might be intuition at a very, very high level of clusters you want to find embedded, but I would start. Yeah.
Mark, in biology, we also do, we don't only do clustering to confirm our intuition, we also do it to build intuition, right? This is also something we do a lot to build intuition, where we're like, okay, you know, like, oh, that particular group of cell is there. Why? And then we look at the genes that are there, and then from those genes, we try to find some semantic of what this might mean in terms of the pathway that are used or whatever. You know, like what I mean here is like we might try to look at it that way. We're like, you know, like here, like the intuition is a bit easier on Drupal. I don't disagree.
I see your point. So you want to have a picture, basically a t-SNE or some whatever embedding of the full network, to see that we have the people that were not onboarded properly, the people that did co-immune, the people, like, to kind of build ourselves an intuition of what underlies the data and see how it varies by removing some layers or including some layers. Yeah, I think that would be an easy thing to do as a way to kind of explore.
I don't know. I feel like Raskin, this might be something that interests you to do, actually, or could be a good exercise for you.
Okay, I have an example prepared about analysis, social network analysis. At the end, maybe that I put it there thinking that it would help maybe launch a discussion more related, yeah, to the analysis of the Juggle network, more than the actual recommending.
Pedro, I had two questions, if we still have a little bit of time. The first one was having to do with the embeddings. So the embeddings are calculated just using the topological properties of the network, or also some explicit data produced by the users, for instance.
Normally, but I think there must be also embedding of scores, for example.
Yeah.
If you have a weighted part, a weighted bipartite graph, there's surely someone embedding those scores too.
Okay. And then my other question was, I saw that you mentioned random walk in relation to the metapath in method number 2. Is this something that is taking place in HinPy right now?
Taking place where, sorry?
In the similarity cluster search and top key extraction. That's a completely different algorithm than what we see in HinPy, right?
Yeah, HinPy only provides the random walk part.
Oh, it does.
And some other things, but for example, I've done. I'll show you at the end also a clustering example. Like for example, you would do some random walks, and in here you could produce probabilities for users and then cluster in the probability space to detect clusters of users. That's something that it's very normal. A lot of people do it, and I could show you an example at the end.
And what kind of limits are placed on the time spent walking randomly? Do you have like because I didn't see any hyperparameters related to the random walk.
Maybe I missed the first part of the question.
Yeah, I was wondering because you can walk randomly, for a long time in the network, and I was wondering if there were any hyperparameters that specified some bounds to that type of processing.
Yeah, I see what you mean. In here, what you have when you say random walk is the theoretical result of the random walk. You see it as a stochastic process, and you compute the probabilities of the end of the random walk. You don't simulate random walks actually.
Ah, okay. So
random walks are a way of accounting for what it's inside inside of this chained topology.
I understand. Okay, thank you.
Thanks for asking that question. Like I was also curious, but like I just thought it was a dumb question.
Mm-hmm.
Yeah, actually, I spend so much time on the week on these things that I haven't even noticed that it wasn't evident, but it isn't. Yeah, this is our theoretical results of the random walks that allow to exploit, to provide a proxy of all this chain of bipartite graphs.
Mm.
And it's going to provide something that is related to the topology in it.
Awesome.
So in here, there are not great books because it's a very ongoing thing, but there's these lectures that are good. There's also this article, which is very central to what people in the citation network, what people refer to skip some ideas, and a lot of ideas used are in here. But it's a very computer science community. So there are always 8-page articles and definitions of 2 lines. So it's not a lot of definitions and not always satisfactory. So it's a very ongoing thing. And I think I also already shared this, which is a compilation of different papers that come all the time from this top conferences and the code also, which is very useful. So how to evaluate these things? So the first thing that comes in mind is the prediction capability, the accuracy, and the accuracy of what the distinction normally made is between these 3 things. So you have your data, which is your heterogeneous information network. So it's collaborative, but also you have your structured metadata on users and items and other things. So you first produce a model, and that model allows you to do the building block task like link prediction or score prediction. And you test that with metrics like this if it's score prediction, on metrics like this if it is predicting some binary thing like a link exists or not. Someone has chosen a thing or not, and you test it in your test set. So in here you have your model that could be, for example, clusters or an embedding. And in an embedding, you test for a threshold of distance between items, and you said that is your production of links, prediction of links, and you test for these things. So the next step is to extract a list of recommendation and test the accuracy of that list. And for that, there are a lot of different metrics that are related to testing the quality of a list of things, and are very related to already existing metrics in information retrieval metrics. And then finally, there's this thing we have also talked about, is usage. So you had your way of doing your model, you're producing lists, you send the lists out there, and how you test them. These are the dominating two. By the way, here I'm not an expert. This is what I see as a useful framework of organizing what it's out there. I think that 80% of the things you're going to find out there in papers are in this table. There are a lot more, but these are definitely the ones that pop up the most. And what's important here is this division in three parts. So we would have our, for example, in Java, we would have our hint. We would do scores, and we want to check if we can predict scores. Then we would have lists, and we would try to test, for example, if things recommended in the email sent, if we send 3 things, how is the quality of these 3 things sent? And then if people actually clicked on it, or if clicking led to their entering and using the platform in some way that it's a catalog label as a success, to tag that and keep track of this. This is the 3 worlds of evaluating the recommender systems.
I see. What's the difference in the session success rate and click-through rate? What's the session success rate?
Click-through rate is the amount of clicks that use a link, and session success is establishing a criterion for the success of a session and labeling sessions as success or failures. So for example, if you enter recommendations but you don't follow through, maybe you want to count that as a failure, for example.
I see. Very good. I understand. In our case, it would be like you clicked, and after that, you actually commented and solved the need, for example, or
yeah.
I understand.
This is how many times, this is labeling each session as did it work or not as you wanted.
This is very nice. Thank you.
And all these papers are very, very homogeneous. This is a very cohesive community. And if you look at these papers, a lot look the same. They have some data sets that are some heterogeneous information systems. They don't change that much. If you change data sets, it's not that good, because it's they count a lot of comparison. So these 3 are very repeated data sets in papers. So you specify your algorithms. You say my algorithm is better because it exploits some other thing, of some other mix of random walks or parameter tweaking. Then you explain what are you going to test. For example, in here, you specify for each data set your metapath, or the metapaths you're going to consider in your weighted optimization of the mix of the metapaths. And then you report a huge table in which you report your predecessors and you say, okay, I'm better in this, in this, in this, and this. And this is a community that is very aligned in industry, with industry, and they are very focused on marginal changes in this accuracy metrics. So
I think you described the whole field of computer science today.
There's some part of it. This part of the top journals, top conferences, very like that. Yeah.
Wow.
So there's this thing, this movement, which is a lot slower and there's less people working here and it's a lot less structured about other qualities of recommendations beyond accuracy, because early on, also about the group lens, it was acknowledged that it was not only not enough in the sense that we are lacking something, but it was also producing some problems. So for example, if you do extremely accurate recommendations, they will often prove to be not useful because they will be redundant. Typical examples are you enter in the Amazon and if it was purely accurate, you would see like all the books of Harry Potter. Lots of people have all the volumes, so I don't know, 7, 8 to 10 volumes of Harry Potter. So it's not useful, it's redundant. Other thing is lack of exploration. You could be leaving clients, because this is a very industry-driven research, you could be leaving clients blocked out of a lot of products. And you could also produce things that are obvious. There are a lot of products that people don't buy, and they don't buy it because they don't know them. It's because there are books that they read like 10 years ago. So if you're shopping for books, there's no sense in recommending them. Like everyone should be recommended Dostoevsky. Yeah, but no one's buying those books because they all read it like in school. So the problem is in the academic discussion and the papers is how to define the properties that could account for this phenomenon. And there are a lot of names called serendipity, novelty, discovery, courage, diversity, self-information. There are quite a lot, and they're not very consistent between them. So this is very much an open debate, and different people in different industries just choose one, tweak it for their needs, and go ahead. There's not a unified vision of what they should be. And in this paper that has very few citations for the usefulness it represents, because it's very useful, it's a compilation of all the metrics that are out there for these concepts, which is not consistent even at the level of name. Like a lot of papers propose novelties that have different formula or different concepts even behind. And what they all boil down to is these two things, but there are some others. And basically it means if you have an HIN schema that is like this, like users, items, and types, and there are links that are things you have recommended, and there are links of things people have chosen. So a diverse recommendation could be, for example, if in the things we recommend to you, these items are very different with respect to some top typology. So if you're in Amazon, for example, and you have 5 items recommended to you, if they all belong to the same type, it's not diverse enough. So engineers tweak ways of imposing additional diversity in this sense. Another sense is similarity based on what people have chosen. So, for example, if you were proposed 5 items and these items were all previously chosen by the same group of people, they could be deemed too similar. So we would want to impose additional diversity in this sense. And these first two, they boil down to computing similarities also in matrices. So for example, here you would have a matrix of items and types, and you could compute row-wise cosine similarity to decide the similarity between 2 items. Or a bipartite here to compute similarity of items according to what people have chosen. And there are some other things that are, there's a lot of ecosystem of things, but none of them is widely used. For example, keeping tracks, there are systems for keeping track what you've seen, what you've liked, the probability of intersection, and if it should be shown again. All of that you can check in this paper, but it's not very useful, I think.
One question, well, I can go and read the paper. What I wonder is, I guess from person to person, that serendipity level might not be the same, in the sense that some people really want to do a random walk across all types of things, and that's what, you know, keeps them going. Some people like to be in the bubble and really want to dig deeper in the bubble. And I think we'll talk about that maybe at the end, but this is kind of the feedback and personalization aspect of the coefficients involved in these recommenders, right? And how do you use the success rate to kind of feedback on the recommender itself?
Yeah. For example, I've seen some prototypes in YouTube that in which they forget about defining these things. They have just one metric, which is hours seen by month, and they plow through, and the recommendations adapt to what makes you watch more videos. And for some people, that means that the parameters of the training of the model trained are going to be more diverse, or more bubble. Like, for example, it happens to me that there are some clicks that I like to see over and over again, and YouTube understands that it's coded somewhere. If people were interested in the explicability of the model that resulting from my training, maybe it's explainable that some things resembles to serendipity 0 for that kind of video.
So in a way, I guess if they do this one objective function, it's very nice. It's like an energy in physics, and they basically do a simulated Monte Carlo, or a simulated annealing, right?
Yeah.
So they're trying to maximize that, and they bring some serendipity to make sure you're going to the other local maximum, so that you can keep exploring. Okay, that's interesting.
And beyond this discussion that began in 2000 and early 2000s, there's all this other part about the societal impacts, filter bubbles, you know, the filter bubble effect, and this book that very launched the subject into the public debate. And there's a lot of computational social science literature on the supposed tendencies of YouTube to showing you more and more extreme views, or if Facebook is isolating you from views of because you're in your bubble, and etc. So there's a lot of research on trying to define what diversities could be in this community too. This is the presentation of the article that supports the computations done in HinPy, in which what we did was a proposition of how this debate of diversity should be structured. So what we did was, it's in here, I think I showed it to you, some kind of a bottom-up construction of what it should be. So for example, this article, which is very fascinating, it's a very weird article, very long, and it has reviewed a lot of results from a lot of different domains to try to establish what it is, this diversity thing that is so used in some academic domains, but also in public policy. And it goes into a lot of depth to show that it actually refers only to three things: diversity, variety, disparity, and balance are the properties that are behind the meaning of diversity in the use in academic literature for the last decades. So what do they mean? So here, for example, you have a situation where you have five kind of things, and the green kind has more things than the red kind. So a more balanced situation would be a situation where they all have the same number of things. Each type has the same number of things. A more varied situation would be regardless of how many items you have in types, if you had more types. And yet a different kind of diversity would be disparity, where it doesn't matter how many types or how many objects are classified into types. It only matters that types are different among them. So this is what it's behind entropy, Herfindahl index, Gini index, and a lot of examples in a lot of domains. So trying to frame a bit more that concept, what you have is things classified into types here in bipartite. For example, in antitrust, you would have units produced by firms. You compute in here something, and you apply the Herfindahl index. Income in persons, Gini, individuals in species, Shannon evenness, or Berger-Parker, or richness, or in computational social sciences, you would have normally entropy of the entropy of the distribution of reads of different news outlets, for example. So in a more general sense, you have items classified into types, and that induces a probability mass function on the types. And what diversity measures are functions that take this probability mass function and produce an index, a probability diversity index. So in the review of what all these diversity variants had, they had a lot of properties, and if you code each property in an axiom, for example, symmetry, you want it to be blind to types. If you change here, for example, one person and another, but you keep with their salaries, for example, you don't want it to affect the diversity measure. So that's symmetry. And properties like that, very simple properties that are proven to be in the article, very well captured by only one family of functions that is parametric, that has one parameter that modulates the importance given to variety and balance. So here's, for example, the same function that it's called true diversity for historical reasons, because someone in ecology called it like that a long time ago. So if you choose the parameter to be 0, 1, 2, infinite, you recover exactly different metrics that are very widespread in different domains. You recover Herfindahl index, Berger-Parker, Shannon entropy, and all of those.
A lot like the Thalys entropy, no?
Thalys entropy?
It reminds me of that, but I don't remember exactly. You know the Thalys entropy?
No, it rings a bell. Let me check.
Generalized entropy, which is also one parameter and is reduced to the Shannon entropy when the parameter is 1. Let me look.
How's it written?
Thalys, Tsallis. It's almost, yeah, it's a bit, it's very similar. It's very similar, but not exactly the same. Not exactly the same.
Okay. Well, in the article, there are a list of all the things that belong to that family.
It's also the participation ratio in quantum physics with alpha equal 2.
Okay.
Which is used to analyze the participation of different entities to different energy levels in a Bose condensate.
That one doesn't ring a bell.
Inverse participation ratio. It's a quantum physics, like quantum specific.
Maybe I'll take a note to put it in the article after the reviewing process.
Very good. Okay, so you're showing diversity as a function of the parameter.
If it's proven to respect the axioms. So here, for example, to give a little illustration of what it looks like, here you have the parameter, here you have the value of the diversity, and here you have some distribution, some probability mass functions resulting from some classification. So for example, in here you have four probability mass functions that have 6 types, and they are growingly unbalanced. So alpha being larger means giving more weight to the balance property. So the larger the alpha, the faster the diversity falls when a distribution becomes unbalanced. And the smaller the alpha, the more they converge to 6, which is the number of types they have.
Yes.
So
and the types, remind just the slides before, how you define the types here.
It's the types, you have your data, you define your ontology, and then you compute your classification.
But it can be an emergent thing. It would be the bubbles, for example, like it's a coarse-grained typology that you have defined yourself on your data.
Yes, it's whatever typology you had defined.
I see. Okay, I understand.
So this is the proposition of the article for what diversity should be, because it's very easy to extrapolate and exploit the semantic tools that heterogeneous networks offers. For example, here you have a simple heterogeneous information network. You have users that have rated some items that belong to some types. And here you can produce, for example, a collective apportionment across a metapath. So in here you have, you start randomly at users and you have your distribution and you compute your diversity. Or you could start at an individual and compute its diversity. So these are semantically meaningful observables in this complex system that are represented by these arbitrarily large and complex heterogeneous information networks. And the thing is that these are not only observables to observe diversity of what have been chosen before, or according to whatever semantic encoded in whatever metapath. It is also things that are at the core of the computations done by these recommender systems based on heterogeneous information networks. So here, for example, if you compute the apportionment of users going to items, going back to users, and then again to items, the ending probabilities here resemble a lot user-based collaborative filtering. Because in here, items that have higher probability are going to be items that are chosen by users that have chosen the items that you choose. So in producing these observables, you also use things that encode collaborative filtering, and it is the way in which this modern recommender system that do large embeddings encode collaborative filtering. And the content part is it's a lot more obvious, and it's a lot of what we've been doing in Juggle, I think. I don't think we have been doing collaborative things on metapaths, right?
Well, you could, not yet, but you could say that if we did user to user recommendation based on skills. Yeah. But right now we did not do those. Or we could do project similarity. All the horizontal one will be very much like that.
So what it's in the article, it's a formalization, the framework, and a formal language to name and compute all these observables, and how to use in diversities in fields that are in need of these definitions of diversity. The first one is recommender systems, but there are a lot of others in ecology and economics. And what the module does, what Python does, it does recommendation just because when it was coded, it was needed for experiments. But what it does is to compute these apportionments. It's a syntax for operating with heterogeneous information networks, a benchwork for doing things with it, and computing these apportionments, which are the tasks that are needed for these observables in the systems and for recommender systems. So here I try to put everything in one slide. So I think it's useful to think of data structures that are at least friendly with this, in meaning that it could be easily extracted, something like this, so that a lot of code that it's being done out there in this top journals and top conference could be recycled and used. And does that not hinder the possibility of using the classic things that are already coded in Surprise, for example, which are very easily implemented by extracting some part and using some topological and metrical recommendation that allows for mixing the metadata and the collective parts to do recommendations, and recommendations really boil down to find similar things, be it because you have embedded and do some training on it, or because you explicitly look for clusters to find similar things, then to produce ranks. It all boils down to find similarities, be it in a topological setting, metrical setting, or in some embedding if you want, recommending. It all boils down to this, and this I think it's a much more sensical definition or taxonomy of what recommender system should be, instead of the old recommendation. And the object here is the metadata, because it allows the mix, the bridge between a semantic and some computable object. And for the evaluation, I would say there's the model that has to be tested for accuracy. There's the recommendation itself, aside from the issue of seeing and evaluating what's happening once you launch it. And then in here, we don't want to get too lost, I think, in accuracy, especially when you don't have a strong signal in which you trust. Because if you have years and years of past data, maybe you can do and test things that if you launch yourself in a very normative setting, which you're trying to optimize for accuracy, you're very much forcing some kind of dynamic that is maybe not the one you want for the future. So for the question of how to treat and use diversities, be it to improve or test our recommender systems, or even in the meta studies part to produce an analysis of what is the evolution of a community that is doing some collective task, I think this is at the core of the project that inspired HIMPI, to produce easy to use observables on these kind of complex systems. Mm-hmm. So here, for example, I put one illustration. Here I put just a quick things from the README, like this is the spirit of the thing. That you have your network, you have your file, and then it's as easy as produce the apportionment for this path. For example, in here, if I start here, I follow E0, E2, E4, I end up with an apportionment on the ending part. Or if I want all the individual apportionments, I do in the proportional abundances. So here, for example, one simplification that we could do is just to produce the proportions of the ending part of some metapaths. And the observables, there are many, but here I put just some examples. For example, one is the entropy. So this is the entropy of the choices of V5 made by V0 through this path, or more complicated path that could have some inverse links, so as to account for things like collaborative action. Or two, I put this example here because this is something we have talked about in the past. Producing here a probability mass function could also be used to do weighted means. If you had, for example, for this person, some probability mass function here, and you have values in here that could be project success, project members, some other quantities that are proper to these entities, you could use the probabilities to compute some weighted means. So there's a very easy semantic to do that. This is one example I use that are using people in Media Lab to analyze a community of people that move in different platforms. So for example, you have Twitter accounts that produce tweets that have some links. Those are also links using Facebook posts that are produced by groups that live in some parts of the country or that are associated with other characteristics like size of the city in which they live. Some NPL tasks produce subjects. Anyway, like a complex evolving network of people doing things. So for example, they use HinPy to produce, this is the collective apportionment of groups into topics. So it's something like the attention given to topics through publications and the evolution in time. They compute that for windows of time. So another thing, for example, if for every group you compute for that apportionment diversity, here you can follow the collective diversity, which is something like how many topics groups as a whole were talking about in their publications, accounting for these two properties, diversity and balance, and the distribution of individual diversities of groups. So here, people talk more or less about 8 to 10 topics, but at some point, groups began talking a little less topics, then to regain some diverse topics. Anyway, it shows you the evolution of the observable of these complex systems. And here is, for example, the distribution of pairwise metrics in the probability space. So each group here has a probability mass function here. So at any moment in time, you can produce pairwise, the distribution of the pairwise distances. And here is as a Jensen-Shannon distance in the probability space. So groups were somewhat dissimilar, and they became very similar at some point.
Mm-hmm.
So that here it means they were all talking about more or less the same things.
Yeah, I see.
In the same proportions. And here I included finally other examples that are more related to producing recommendations using HinPy. Well, here, for example, this is the movie lens data set. We have users, occupations, gender, location, age, films, types of films, years of release. If they rate it, this is weighted. If they like the film, and this is another one produced with recommendations that then we can use to compute diversities. The diversity of types of films through the recommendations of films made to users, for example. So in here it's a setting which is very similar to Juggle. So you choose some meta paths that you're going to use in a recommendation. So in here we want to recommend items which are films to users following two meta paths. One is here, for example, gender or location or whatever. One related to user in a path that would follow, that would touch that part of the content and end in films, and another one using some metadata on the item side. If here is, for example, if a kind of a type of films, there's horror, comedy, or whatever. So you have a meta path that touches that, and you mix the probabilities resulting from these two, and you modulate it with a parameter here called badly alpha. And here you would test, for example, the F1 score, depending on the number of things on the list you recommend to people. So in here, for example, is the accuracy, the F1 accuracy, if you use location and type of film for your two meta paths, and modulating which weight to give to each one of these paths. So here, for example, these are very poor recommendations if you use occupation and type, but if you use location and type, recommending a set of 5 items to people, you would produce very good quality in the accuracy sense of films. And likewise, you can use, after you have computed this recommendation link using this, you can measure the diversity. For example, in here, it is the user item genre metapad used to compute the diversity. So the collective diversity and the mean individual diversity.
Okay.
And this is
it's a huge slide with a lot of things together. It's pretty late already. And could you give the take-home message of this slide? And I think also people have to leave soon. It's already 6:30.
This is the last slide.
Okay, cool.
This is the last slide. So this belongs to a paper that it's upcoming, and this looks a lot of what it looks like what it is to test the accuracy of a recommender system, like the one we are implementing in Juggle.
Okay, and
this is the kind of things we would be seeing if we wanted to test in a normal way our paths, curves of accuracy.
And accuracy is based on the existing network?
Yes.
Okay, I see. And the diversity is based on types that you have defined. Oh, the type. Okay, so you have defined the types there. I see.
And this is from a paper that's not yet finished that I put it here because we talked about this once, about simulating things rather than testing things with the data we have. So in here, for example, there's an initial state. Using this, I recommend one item to each person. I make them adopt that. And I run this in cycles, in iterations, adopting each person adopting one item and following what happens to collective diversity and individual diversity. Here it is for the very classic collaborative filtering things, user-based, item-based, and here is using the kind of recommender system that Juggles uses. So this looks more like something, some kind of simulations we would want to do in Juggle to test where this recommender system could lead us.
So what would we need to actually simulate things in the sense that would you take the same type of network and take the same type of degree distribution and explore based on that, like to create null networks or simplified null networks? Just what would be a way to, or you would take the existing network and try several rounds of recommendations and actual engagement, or what is the way to simulate exactly?
The most straightforward way would be to take the network as it is today as an initial state and simulate recommendations in cycles and producing the same curves.
That certain proportion of these recommendations are actually followed, basically.
Yeah, the difficult thing is to take into account all combinations. And the other difficulty is if we want to simulate with the current state of the network, or we want to produce some set of possible initial states that are credible or representative of something beyond Juggle. If you want something like collective learning, collective tasking, these are the types of networks that would represent a normal team. We launch recommendations on all of them. This is what we see.
I think for now we have to stick to Juggle. I mean, we can think of other data sets afterwards to train on. I mean, maybe I don't know all the data sets on that. What I think is important is to kind of build intuition on certain things here, because there's many things in these networks like heterogeneity in the degree distribution, for example, that can make some effect of popularity, breeding popularity, or things like that. So, you know, some effects we might also want to not necessarily, it's not just about diversity, there's some effects we might want to take into consideration as well. Is it the last slide, by the way?
This is the last slide, yes.
Okay, great. So first, I mean, it was really, really useful actually to see the overall work. It was really a great presentation. So thanks a lot for having done that. I think it's also useful that we record it, and that maybe if you can share the slides on the GitLab or on the Slack, it would be useful for the other to catch up.
Yeah, definitely.
And so I understand better the whole thing. If there's only one thing that I feel that probably people are working on in a way is how you continuously learn from the monitoring, how you create a system where the metapaths are learned and the weight of the metapaths are learned themselves from a mix of like diversity plus accuracy, right?
Mm.
And that's because right now we're going to put some weights and we're going to decide very top down on some metapath, but there might be other combinations that are much better at improving over the SSR that you named, as well as diversity, and that would be for me the kind of line of work that would be the extension of what you've shown us in a way.
Yeah, I'm not an expert in the literature, but I have the feeling that if I haven't seen it, it's because there are not a lot of things about it out there.
I would just try to give a look at the deep learning community, because I would be surprised people haven't done some kind of way to back propagate the observations to
yeah, there has to be something, but what I mean is that it's not
not obvious.
In the RecSys papers, in the RecSys journal, you don't see often things like that.
Yeah,
that's my feeling without being an expert.
It would be useful to try and think in that direction. I think now the step we're going to do now in any case is that we're implementing simple ones, and I think it will be useful to think of what would be a perplexity in Juggle and a diversity, and what types are we going to define to compute it. And it can be based on programs or SDGs, or we have to define of something, or skills maybe, and see how it evolves and monitor that in time. The next time we'll have Roby that has more the social science paper, so that can help us maybe also craft a bit better, like the measures of success and measure of performance that we need to define. And during that time, we can prototype the first stage. But so based on that, based on your last slides especially, how would you see yourself using Juggle in that context? You talked about simulation, etc. Do you want to already try out with the existing networks to do some work on that?
Yeah, I tried, but there's a lot of work for me to be done, and I haven't found the time to do it in assembling the heterogeneous information level, because there's the API from the Juggle side, but there are also a lot of things from the Slack, right?
I see. I mean, that's true. So the ideal world is that we have the Slack information, and it gives kind of an actual engagement. But the thing is that right now we're just going to do the recommender system will just work on Juggle, meaning that it will not have the information from Slack right now. So you have to assume. Right now, I would say like the focus is on users to needs match, or user to project match, and kind of the idea, like let's say that an objective function would be to say that a project was started and found other members, or like found people that would comment on posts or comment on needs, so interact with needs of that project. Because that's the first thing right now we want to incentivize is the ideation of project and the help in the very early stages of project, and to have further data on engagement in project and implementation and output of project. Maybe we can do that by including the rounds of review, and you have the data for that. Yeah, at this stage, I would try to focus just on user needs matching, probably, because that's what we need to implement right now.
Okay.
And you can get your hand a bit in that. So as I said earlier, the next week we probably have to move the call. So we might actually do that only in 2 weeks, and at the same time, Robbie will be also doing the literature, and I'll ask on Slack. But yeah, so on my end, I don't have really other questions. Are there other questions from the people that are still there? I see Lyuba is still there.
Yes,
or-
actually, I have a question. Yes, it's a very short one. Do you hear me?
Yes.
Yes, okay. Actually, I mean, maybe I missed it, but did you also talk about the time, evaluation of time when you actually send the recommendation? Is there a good literature on that? Because I was interested in that in different reasons, but because your works or your people, when they actually like some things, it's temporal, right? It has a temporal pattern, which is it adds up on complexity on this data which you have, right? So for some people, you need to send recommendation at night, to some not at night. And do you have any suggestions on that?
There are a lot of things out there, but I don't have a structured vision of what they are. But I know a lot of nice examples. For example, in here, I know that some recommender systems are constantly measuring your diversity of music. And when they detect a spike in diversity beyond some threshold, they decide that you have changed the background of that you have changed model, that you have changed, for example, from music you listen to when studying to partying, because people arrive at home with some beers and you want your playlist to adapt to that. So you change one music, one song, 2 songs, that spiked your diversity in a window of time, so it adapts. It says, okay, this person is no longer studying, is doing another thing. So there are a lot of temporal signals like that, but I don't have a clear view of a clear structured view of the research.
But that's a good point, Lyuba. We can keep track of the timestamp, actually, of
Yeah.
and when you were clicked, and just begin by computing a seasonality of that, because I know, for example, that if you post on Twitter, it's better if you post between 8 and 10 a.m. in the morning, or between 6 and 8 p.m. in the evening, right? Because that's when people are coming back from work, or before they go to work and they check them. So we might see that, for example, volunteers contributing to Juggle will contribute in the evening or on weekends, and that's when we want to send it.
And another reason why I ask is because, for example, Juggle really sends, for example, me now as a recommendation for, I don't know, whatever somebody posted on your project, at times when I can't check it, right? And if there would be more literature investigation on kind of human behavior on that, it would be interesting to see. I mean, it's applied to Juggle, to anything. So
it's very much what you know, when Christos came to Crete to give the talk on.
Yes, exactly. Yeah, like for runners application, you know, Pedro, if there are like 2 similar runners, right, for example, and you also may get similar questions on when to send recommendation to run and how it will influence their behavior.
So, but I think the easiest way to begin with that will just be to look at the distribution of people that actually clicked on notification in time of the day and time of the week, and see if there is any pattern from that by the end of the year, right?
This is good approach when you have thousands of users. If you have also thousands, but you really don't have so much time to experiment, I don't think it's a good approach.
No, but I mean, we can already just begin by looking at when people are active on the platform.
Yeah, no, for sure. But I mean,
but I think that's a good question to keep, actually, and to ask if Robbie could inform to us on this kind of thing, maybe, because he's going to do
if you
of things.
And if you also, Pedro, remember about any references on this, because seriously, like when I was trying to help on this recommendation system for colleagues, and I never really found information about, I mean, articles on this temporal aspect.
It doesn't pop right to the eye because the community is very much structured around this.
Mm-hmm.
This is the fight. This is what people are doing to get their papers through the top journals.
Mm-hmm.
This is very structuring in the community.
So could you, by the way, put the literature in a subfolder in GitLab, in the subfolder of the literature folder, so that we can know this literature? And you pinpointed in particular, I think, a review paper that was very useful. I think it would be great if there's one paper that is really useful that you think was really top. It would be great. And if you can also share your slides, I think it would be very useful for everyone. And I'll share the recording later.
Yeah, I'll share it in the Slack.
Yeah.
Okay.
Yeah, absolutely. That was really great. Is there anybody?
Thanks a lot for the
Thank you, Pedro. It was
presentation. I
awesome.
learned a lot.
No,
Yeah.
it was a pleasure.
Yeah, I also learned so much. So really great. Okay, thanks a lot, and see you all soon. Maybe at the global call on Wednesday or anytime. I'll share the recording soon.
Okay.
Bye.
Bye-bye.
Bye.